Okay, hello again. This is week 6 on EE545 Embedded Deep Learning, and this week we are going to conclude our discussions on quantization aware training, in short QAT. Okay, let's start again. So we were talking about this. There was a nice figure I showed you previously. This figure is from MATLAB documentation. It's a very clear figure showing what deep learning propagation training, back propagation training is. So previously we've talked about this. We've made our deep learning systems learn their weights for a specific purpose, whatever it's classification or regression, using this term called back propagation in training. What was back propagation? You had training data. You feed the training data to the network, first the input layer. Then the input layer is being fed to the next layer. Then the next layer is being fed, it calculates an output. The output of this layer is being fed as the input to the next layer. And this operation is called the forward pass. So you do the forward pass for all layers. And in the end, at the output layer, you have a result. And for supervised learning, which we cover right now, we have a ground truth for each output. So just you have the ground truth, which is called the training targets here. By comparing your output value to the training target ground truth, you calculate a loss, showing you how wrong were you when you're making this decision of forward passes. So in the first run, when you're doing forward passes, you either get your weights from a pre-trained network, you transfer them, or you just initialize them randomly using some initialization techniques, which we teach in the previous semester's course. Whatever, now you have a loss. Now using the derivative of this loss, partial derivative of this loss, with respect to the output, then at each layer, with respect to parameters of each layer, we find the derivative of the loss with respect to the parameters of a layer. And using this partial derivative, we update the weights for each layer. That's called backpropagation. We do this iteratively, and we find our weights. So, I told you, if you want to learn training in very detail, you need to take the previous semester's course. In this course, we are trying to learn how to make this training architecture quantization aware. And what we need to understand is only the structural training. So in the structural training, we have these layers here, guys. So for each layer, this shouldn't be here, whatever. So for each layer, we have the green lines, the forward passes, and the red lines, the backward passes. So the loss comes from the previous layer. Then we take the derivative of the loss according to the parameters inside. So, and this derivative continues because this times this is, as written here, this times this, the derivative of the loss with respect to z, the output of this layer, and the derivative of the z with respect to the parameter y is this. So if you multiply them, this will cancel themselves. So you got the derivative of this thing. So it goes on like the derivative flows like this in the backpropagation. That's how it flows, guys. It flows and flows and flows. And while it's flowing, we find these derivatives with respect to the parameters weights, and we update the weights by using those derivatives. Okay, so guys, and we do these in vectorized operations. You remember this figure from Stanford's course. You give a vector of values, you get a vector of values. So you're taking the partial derivative of this output vector with respect to the input vector. So when you take a derivative of a vector with respect to a vector, what you get is called a tensor, which is also called the Jacobian matrix. So you get these Jacobian matrix, and you use these metrics to update your weights in your system. And we've talked about the pseudocode. This is the pseudocode of backpropagation. You initialize weights or you transfer weights, then you start your iterations. So while your stop criterion is false, so as you keep, for example, what could be a stop criterion for a backpropagation algorithm, reaching 1,000 iterations. After 1,000 iterations, you stop. That could be a stop criterion. Or it could be, depending on the loss, it's usually number of iterations or number of epochs, whatever. So inside it, you do the forward pass. Then for each layer, you calculate the partial derivative of the loss with respect to the weights of that layer, and you update the weights. Actually, this pseudocode is the pseudocode representation of this figure. So you forward pass, then you calculate the partial derivative of weights and update the weights. And you do this again. So this graph, this figure can be represented as a pseudocode as shown here. So how to make it quantization aware? We said that if we could quantize the weights, if we could quantize the forward pass, and if we could quantize the activation quantization, it will be okay for us. Well, this was where we stopped. So very natural questions arise here. Are we going to quantize the partial derivative calculation? Aren't we going to quantize the exact place here where we update the weights? Well, shouldn't we? What happens if we do not? These are very nice questions, and actually these are very nice scientific questions, and people have studied it, and we're going to study them today. So how to make it. Now, so in order to understand how to do this, we have to understand the concept of a layer block. Actually, in all different languages, computing languages, we have these different libraries and frameworks. You are using deep learning toolbox in MATLAB, but in our course, you could be using Python and another library like Keras or PyTorch or TensorFlow or Caffe, or you could be programming it in C++ or C++ or Python, it doesn't matter. In all these frameworks, we have this something called the layer block. All of these are constructed as layer blocks. Well, the type of the coding or the type of the data structure, the type of the object, the way it's being architecturally designed can be different, guys. But they all use something called the layer block. So each layer you add is an object or a function or a block in general, we can call it. So each layer block in all these frameworks have these fundamental two capabilities, a forward pass and a backward pass. So regardless of the framework you use, whatever framework you're using, PyTorch, TensorFlow, what you have is a forward pass and a backward pass. Actually, you can write custom layers. And when you write a custom layer, what you do is you define a forward pass and a backward pass. Okay, what does the forward pass and the backward pass do? Actually, you already know this. But if you implement it, yes, you can add these layers to your own graphs, and you can apply backpropagation and forward run to them. What are these forward pass and backward pass?